Hey everybody, so welcome to the first lesson in unit number 3. This is our quantities in chemistry unit. And I'm going to introduce you guys to a topic today, probably one of the most important topics in chemistry to be honest with you, and that's called the mole. This is going to be the basis of understanding the remainder of the year, so today's lesson is super important. So how do we interpret a quantity? Well, it turns out that we oftentimes make up special units to help us understand quantities in chemistry, or pardon me, I shouldn't say in chemistry, in everyday life. And we've done the exact same thing in chemistry. And so we've created a special unit called the mole. Now, what other units that are not the typical SI units do we have? So I have a whole bunch of examples of these, and here we go. A bale, for example. A bale is a large bundle of goods. In the United States, it weighs about 500 pounds. It represents about 500 pounds of cotton. That's what we would call a bale. So that is a special unit. The bale is a unit. So if I say I have 2 bales, I have 1,000 pounds. If I have 5 bales, I have 2,500 pounds. You get the idea. What about a carat? Well, it turns out that when we're talking about a carat, we're talking about 200 milligrams or 3.086 grains troy, which is another measurement there. They use carats to measure how big a diamond is, but when we're talking about it, we're really just talking about weight. It's just we use that to help us understand and to use smaller figures. So instead of saying I have a diamond that's 450 milligrams or 500 milligrams, I can just say I have a 2 carat or 2.5 carat diamond or something along those lines. Horsepower, so you oftentimes hear horsepower with cars, or motors will oftentimes have a horsepower rating. 1 horsepower is the amount of power that you need to lift 33,000 pounds a distance of 1 foot in 1 minute, or 11 over 2, or 5.5 times the amount of a horse in terms of the actual weight or power that horse has. Again, we use it to measure the power of our engines. A span, so when we're talking about a span, we're talking about 9 inches, or roughly the distance between your thumb and your pinky finger. An acre, that is roughly the amount of space that a particular yoke or oxen could have plowed in one day when we use those things. Of course, we don't use yoke or oxen to plow land today. We use tractors and other things like that. But an acre is 43,560 square feet. And that's where these arbitrary units had. So if you had 100 acres, then you would need 100 days with 1 oxen or yoke to plow that particular land there. So there are other common measures, things like a gross. So a gross is actually 12 dozens or 144. A ream, you guys may have heard of a ream of paper, for example. We're talking about 500 or something. Or a stone. Stone is used to measure weights. So if you watch like the World's Strongest Man competition, they'll tell you how many stones they're lifting. 1 stone is equivalent to 14 pounds. And there's some other ones that you guys might be familiar with. So for example, you guys know that dozen represents 12. A baker's dozen represents 13. These are all arbitrary units. They're made up units that have no actual use other than to help us count larger numbers of whatever it is that we are counting. So this slide, I know it seems a little daunting, but this slide actually shows us a couple of things. If you look along the left-hand side here, it gives us all of the prefixes that we would add to something in order to represent that particular amount of that particular substance. So for example, kilo, you guys are probably familiar with, kilogram, a kilometer, all of those are in thousands. So a kilometer is 1,000 meters. A kilogram is 1,000 grams. You guys get the idea. And there's some other ones here you might be familiar with. Milli is 1,000th, or micro is a millionth, or nano is a billionth, etc. So you guys get the idea. And this is just a reference slide. I'm not asking you to memorize this, but understand that if we are talking about quantities and we use these prefixes, you may be asked to know what they are. And that brings us to the made up unit, or the arbitrary unit for chemistry, and we call that the mole. So when we talk about a mole, I really want you guys to visualize a dozen in your head. So when I say to you, I have 1 dozen of anything, I have a dozen of this pen that's sitting in front of me, or a dozen of my TV remote that's sitting in front of me. All of these things represent the same quantity. So if I have a dozen pens, I have 12. If I have a dozen, remote controls, I have 12 of them. When we're talking about chemistry and the mole, a mole just represents a quantity of something. So a mole is a unit of quantity. So if I take a look at this particular very simplified reaction here, of course these aren't the correct chemicals here because we don't have subscripts under the chlorine. But if I look at this, it says sodium plus chlorine produces sodium chloride here. You'll notice that in front of the sodium, in front of the chlorine, in front of the sodium chloride, there aren't any coefficients, but we know that there is a coefficient of 1 in front of each of these things. That coefficient of 1 also means not just 1 atom, but it also represents 1 mole of quantity. So if I have 1 mole of sodium plus 1 mole of chlorine, I will produce 1 mole of sodium chloride. So when we look at the combination here, it's a little bit odd because you're saying to yourself, okay, I have a mole of this and a mole of this. Why don't I have 2 moles of this? And that's because we're actually sticking them together. Here's a good analogy. If I had 12 burgers and 12 burger buns, how many completed burgers could I produce? And the answer is 12, right? You stick your patty in between the buns, you still have 1 completed burger there. Even though we had 24 entities to begin with, we now only have 12 in the end. Same kind of deal there. Here we've stuck the atoms together, and so we're talking about 1 mole of this particular substance. Now, in terms of how big a mole is, well, a mole is a constant value. So whether we're talking about a mole of this pen or a mole of atoms, we are talking about the same quantity. So when we look at determining how much is actually in a mole, we look at the carbon atom as our standard. So if you look at the periodic table, you'll notice that the mass of carbon on the periodic table is 12.01 atomic mass units. It also represents the mass of carbon if I had 1 mole of carbon atoms. So let's say I had this arbitrary number, this quantity of carbon atoms, which represented 1 mole. If I took 1 mole of those atoms, remember a mole is like a dozen, if I took a mole of those atoms and I placed it on a scale and it was carbon atoms, it would weigh exactly 12.01 grams. Or in other words, it has a mass of 12.01 grams per mole. If I take any other element on the periodic table, so let's say I took hydrogen, for example. Let's say I took another mole of hydrogen, that quantity of hydrogen. If I took that quantity of hydrogen in terms of the number of atoms of hydrogen and I placed it on a scale, it would weigh 1.01 grams in every mole. If I had, I don't know, pick another element. If I had sodium and I took 1 mole of sodium atoms, I would have 22.98 grams in that 1 mole, grams per mole. So basically this means that the atomic mass units, which is the protons and the neutrons put together, will always equal the mass in moles of that particular substance. So the number of carbon atoms was calculated, and this is what we would consider to be called a mole. It was calculated by an Italian chemist named Amedeo Avagadro, and he determined that the number of carbon atoms in 12.01 grams of carbon is equal to this enormous number here, 602 with another 21 zeros following. And this is what we call Avogadro's number. Now, for simplicity's sake, we don't obviously want to write out enormous numbers like this. We want to simplify them. So we are going to use our scientific notation. If you are unsure of this, on how to do this, the decimal in this large number up here, Avogadro's number, is actually following the last 0. And so what I'm doing is I'm taking the decimal and I'm moving it to the position before the first non-zero digit, so right before the 6. And as I do that, if I'm moving my decimal left, then I need to have a positive value in my exponent down here. So 6.02 times 10 to the power of 23 takes this decimal, which you see right here, and moves it 23 positions to the right. And that's what is represented by 1 mole. So if I had a mole of this pen, I would have exactly that number of pens. If I had a mole of this particular remote that's also in front of me, I would have that many. If I have a mole of atoms, I have that many atoms. So Avogadro's number is approximately a million billion billions. It's an enormous number. To get an appreciation of how big and enormous that number is, the United States spent a trillion, if they spent $1 trillion in 1 year, and you actually had Avogadro's number of money, which would be an enormous amount of money, you could spend $1 trillion every single second for over 10,000 years, and you still wouldn't reach the necessary amount for you to reach that Avogadro's number. It's just an enormous number. It's an unfathomable number. I do have a lovely little story that I will read to you guys on the next little slide there. It's called the green pea analogy. It's a wonderful little one here. In any case, it also allows us to determine the molar mass for each element on the periodic table. When I say molar mass, I mean how much does 1 mole of that particular element weigh. So as I mentioned already, if I look up on the periodic table, I'll find sodium, for example. Sodium has a mass of 22.98 atomic mass units. It also means that I have a mass of 22.98 grams per mole. 1 mole of sodium weighs 22.98. If I was looking at chlorine, maybe we're interested in the sodium chloride there. Chlorine, if I look it up on the periodic table, has a mass of 35.45 grams per mole. Grams if I had Avogadro's number of atoms of that particular element. Now, if I'm interested in finding the molar mass of a compound, I just sum the two together. If I have sodium chloride, for example, I have 1 sodium and 1 chlorine. Sodium weighs 22.98, chlorine weighs 35.45. We add them together and you would get the molar mass of the molecule. Now, there are some interesting calculations that you can do with the mole, and these are the equations for them. So I can actually determine how many particles I have by taking the mole, which is represented by the lowercase letter n, and multiplying it by Avogadro's number. And the reason that I can do that is because the units for moles is just the mole, and the units for Avogadro's number is grams per mole. And so when I particles per mole. And so I end up in a situation where if I cancel out the moles top and bottom, I'm just left with number of particles. And then of course down here, I also can do a reverse calculation. I can take the number of particles, I can divide it by Avogadro's number. Particles over particles per mole will produce the number of moles for me. And so that's the end of the initial lesson, and I'm going to do some subsequent lessons for today's topic, and I'll post those as well. Thanks, guys.